In this video, we're now going to the second sort of method of prediction. We'll address first of all the prediction problem and then the control problem that kind of naturally flows after Monte Carlo, that is called temporal difference. And this is a kind of an important category of methods that I think they are going to at some point merge together with other approaches we have seen in solving, if you like, a bit more elegantly the prediction, the value function prediction problem. We have seen in the Monte Carlo prediction that the Monte Carlo kind of a value function update is as follows. Let's say V pi plus t is equal V pi of st plus alpha, the return after this state minus the previous estimate st. Okay, so this is what was happening in the Monte Carlo approach. And what we actually is happening in the temporal difference is that, again, of course, this means that we have to wait until the actual realization of the episode kind of happens and all the experience kind of formulated within the episode until we are able to update this kind of value function. In the temporal difference, what we actually do is we have another sort of what it turns out to be an advantage is that we don't have to wait until the episode completes, and the equation becomes V pi of st is equal to V pi, capital V that is, of st minus, plus alpha of the following. This is RT plus 1 plus gamma V of st plus 1 minus V of st. Now, so what is really the big deal about it? You can consider the temporal difference learning approach as some kind of a hybrid between what we are doing in Monte Carlo and what we are doing in dynamic programming. And in the dynamic programming kind of video, we have seen that there is bootstrapping, and here you see the bootstrapping in front of you. So we are using the value function of the next state and its estimate, if you like, in order to bootstrap the value function of the state that we are interested in. And at the same time, we are effectively maintaining the sort of the Monte Carlo kind of approach, in the sense that we are still generating, if you like, experiences that we would like to consider in that evaluation. Let me write this down. The so-called one step, more specifically, we'll refer to this as TD0 temporal difference methods, combines the bootstrapping of dynamic programming and the sampling of Monte Carlo. To give you a kind of an example from real life that you can always kind of refer to and kind of map it to that kind of equation. So let's assume that I'm coming from Brooklyn. So let's call this the SB, the state that I am in Brooklyn right now. And at some point I need to go back to New Jersey, and therefore I have two options: either to take an action to go through the Brooklyn Bridge or to take another action and go through the Manhattan Bridge. So that's my A1 and A2. And A2 is Manhattan. And let's also now define two other states, the past Brooklyn and the past Manhattan Bridge states that I end up after I kind of crossed those two bridges. So just like what happens in kind of real life, the moment you go through a kind of a significant kind of milestone in your commute, let's say crossing a very too busy kind of landmarks over here, then you can actually update your estimates. Okay, now that I have passed the Brooklyn Bridge, now I have another 40 minutes to reach my kind of destination. Then that is this value over here. The fact that you can now update the SB using another guess. So we are effectively estimating using yet another estimate, and this is basically what the bootstrapping is. So we kind of receive our reward here, which is this. The moment we sort of pass, we actually taking this action and we are sort of landing into these S prime states. And we are actually using the estimates of these states in order for us to bootstrap and update in the estimate of the state. Again, we're doing one step unrolling here. And this is what a temporal difference actually is. So that's so now I think we should come to the discussion as to is that temporal difference method has any other advantage compared to Monte Carlo. Obviously, we don't have to wait until the episode ends until for us to update. Sometimes the episodes are so long that that's a kind of a significant advantage, effectively making the temporal difference method, I will call it as part of what's called online learning. The other kind of significant difference is that it turns out that they do converge into the, so there's not really any issue of using a guess or an estimate to bootstrap and update another estimate. It has been shown, although we're not going to do the any detailed discussion here, that temporal difference methods are converging, and in fact, depending on the setting of this alpha over there, if it is a kind of a small value, it converges and everything is fine. The one thing that you can actually see the convergence is by running an example. In the previous video, we have seen a Markov reward process and using, if you like, two terminal states. And I think it's worthwhile going through that example with a temporal difference now. And we've seen how Monte Carlo kind of approximates the sort of true value function. And I just want to show you the sort of how the Monte Carlo and temporal difference methods now compare. And so this is where the Monte Carlo is, depends on the values of alpha, because we are effectively waiting until the episode kind of finishes. Then we have a significant kind of, I will call it convergence, slower convergence. Okay, so as compared to temporal difference, where actually we have, definitely faster convergence. And you can actually see some behavior which kind of matches the stochastic approximation type of algorithms, like the ones that are those where the lower the alpha is, then we have slower kind of convergence, but then the residual kind of error that we actually get in terms of root mean square error that is between the true function and the estimated value function is lower than perhaps converging faster. And that's kind of a classic behavior with a good trade-offs. But bottom line is that temporal difference seems to be performing better than Monte Carlo methods. Before proceeding into closing this so-called prediction problem with temporal difference learning methods, I think it's worthwhile addressing an enhancement which kind of bridges the gap between what we've seen in Monte Carlo and the single-step temporal difference learning that we just saw. And this is actually called TD of lambda. It's kind of known for with this notation. And we'll see exactly what lambda is in a moment. But the main advantage of this enhancement is that it decouples the sort of actions from value updates. So in the single step process, we are taking an action at every time step, and also we are updating the value at every time step. And this does not really make necessarily the best. It is not necessarily the best choice. We actually may well prefer to keep the actions coming in as frequently as possible, but at the same time to only update states when there are significant updates that are taking place and not every time step. So one small correction I wanted to post on the formula of the return. The right formula is actually this one, and this correction was needed because when we went to episodic experiences later on in reinforcement learning, we kind of discovered that this was an incorrect formula, so there was a couple of typos here. So that's the right one. So I'm going to post that on the MDP section, and we have not really used explicitly this form of that formula anyway in a subsequent kind of discussions, so I think we should be okay. And this is another place where we have actually had a couple of typos on the return. Now when we have an episode capital T of duration capital T, and we are effectively calculating the return starting from when we are at state at time step T. Okay, so that's the second typo over there that we need to be aware of. And this one will actually carry over when we're discussing now the returns for multiple step time the temporal difference methods. So after n steps, our return actually will be written as GT. Let me write it as after n steps. It will be RT plus 1 plus gamma RT plus 2 plus ... plus gamma to the power of n minus 1 R of t plus n plus gamma n V S of t plus n. So I actually wrote also, and then I kind of recorded some other equation. This equation is effectively the one that kind of summarizes how we will actually be using the n-step return in the updated equation for the n-step temporal difference method. And as you can see, the only thing that actually changes over here is that instead of having this term, which is actually we call TD target, we have the nth return, the n-step return in its place. So the n-step return in its place for n is equal to 1. Effectively, it is the RT plus 1 plus gamma V ST plus 1. So we are back into the TD 0, as we'll call it, to understand exactly why the 0, the lambda is equal to 0 corresponds to this case. And that's basically the sort of the end result of the n-step return. So now we can actually decouple the estimate of the value function and the bootstrapping actually we do over there for and the sort of action that we are taking. So we can continue to take the actions at every step, and while we will be updating after n steps the value function. Okay, so that's basically that equation allows us to do so. Now, out of some studies which are not going to be presented here, but they are definitely included in the Sutton's book for those who are interested to deep dive a bit further. They have shown that the way that the n-step what is really the best n to choose. Okay, so it's basically is the hyperparameter, how we actually go about defining this hyperparameter. And what actually has been found is that there are certain kind of trade-offs between choosing the sort of n is equal to 1, the one step, and having large n, as you can understand. And the algorithm that we are effectively concluded out of this discussion is just called the TD lambda algorithm, which is basically what it does is that instead of selecting one out of the n, it tries to average many returns, n-step returns, many n's in other words. So let's call it the many n kind of algorithm or lambda algorithm. And the way that it is being presented is that we are actually defining the average return with a weight that it is negative exponential as it is actually shown, and of course applies up to, it is such that the summation of all the weights in this averaging sums up to 1. And the equation of the weighting of the returns to average them is this equation over here, which is the weight is actually plotted over here on the as a time index, a time step index, up to the, of course, the episode kind of length. And now let's write down the final kind of TD lambda update equation, and also show that with lambda is equal to 0, this corresponds to the one-step temporal difference, also known as TD of 0, and with lambda is equal to 1 is roughly equivalent to the Monte Carlo. So the equation is V, let's say, of t plus n. Since we were also adding policy pi, let's add it. St is equal to V t plus n minus 1 of St plus alpha g t of lambda minus V of t plus n minus 1 of pi of St. Okay, so this is the equation. And now we said that we're going to define also the GT of lambda, which we have seen already. We have seen already the equation. Now we need to show that for lambda is equal to 0, this corresponds to notation-wise TD of 0. The 0 here corresponds to lambda, or to the one-step TD. And so we'll take the equation that we have already quoted. So this is GT of lambda was minus 1 minus lambda summation from n is equal to 1 to infinity. This is n is equal to 1, in other words, lambda n minus 1 GT of n. And we'll write it as this equation here, which is exactly identical to this, but we just changed the notation to be a bit more compatible to the Sutton's kind of book notation, where he is actually using this kind of notation to indicate a return from the returns from t to t plus n. Okay, so this between the t and t plus n kind of a time step that is. Okay, so effectively the returns in TD, in n-step TD, are truncated into two portions. One is really the true returns with all the discounted kind of rewards, and the other is this remaining term or the missing term, which is approximated by the discounted kind of value function. And as you can see from the course side, the notation kind of makes sense, because the GT from t to t plus 1 is effectively what we had for the one step, the t plus 2 for the two step, the three step, t plus 3 for the three step TD, and so on, all the way to the TD infinity, in fact. And we'll see exactly how we will account for that remaining for the terms after the terminating kind of state. We can actually now break this summation over these infinity terms into two parts, and actually this is actually shown over here when we have actually plotted these weights that we are applying into two parts. The first part is what is actually shown here as the white portion, and the second part is what everything is after that, the kind of a shaded region over here. And of course the key term over there is the capital T, which is the episode length. And so what we need to do now is we'll go back to the whiteboard and start, writing a couple of considerations down. So for all indices from n is equal to 1, for n is equal to 1 to t minus t minus 1, the returns are weighted with this kind of decaying lambda factors. I say decaying because, as you can see, it was a decaying kind of geometric progression of that, because lambda is less than or equal to 1. They get weighted with, they are weighted by the factors, the following. So I'm going to take this and break it down into two parts. The first part is 1 minus lambda summation from n is equal to 1 to n to capital T minus 1 lambda to n plus n minus 1 and times g of t plus n. That's the first term, and then we'll see that the second term is 1 minus lambda to t minus 1 gt. Okay, so this is basically the expression, and let me just effectively highlight the following. As we can see, anything that it is, why we actually came to this kind of consideration, especially with respect to the last term over there. So the first thing is that any instant t where we are going beyond, if you like, the terminating kind of state. So anything that it is within this is t plus n greater than or equal to t, or effectively n greater than or equal to t minus t, then all returns are in fact the full return gt, because all the rewards after the terminating state are actually 0, and of course this means that the full return is basically what it corresponds to those cases. So that is the reason why I actually wrote from n is equal to 1 to capital T minus 1, because this is just before this condition gets to be satisfied, right? So it's everything before this state over here that we actually can see on the side. The first factor, the first term, if you like, in this summation we just broke up, corresponds to the weights that we have applied. They're actually shown here in this white region of this, geometrically decaying, if you like, weight curve. And then the last term corresponds to this weight over here, that anything is beyond capital T which is the episode, will actually be weighted by 1 minus lambda to t, capital T minus 1. And that's basically what we also have mentioned here on the side in terms of equation. All right, so this is basically everything that we actually can mention regarding TD of n. This is the sort of n-step TD. And what actually we need to do next is we need to start considering the control problem, and this will be done in a different video.